So how did I begin? All right.
Yeah.
So first of all, I'd like to comment the organizers for not giving up in the face of COVID bifurcation, and for this very nice workshop, and for giving me the opportunity to talk here. So I'm going to talk about driven-dissipative dynamics of atomic clocks. So this is not related to the topic of the workshop, and maybe only in the way that what I'm studying is also zero-dimensional system coupled to an environment.
Which means it's related to the topic of workshop. We wrote that dimensionality doesn't without care. Zero is also impurity.
Okay, yeah, I mean, I would say zero is impurity. Okay, so now this device is a proposal of an ultra-precise atomic clock. So it's supposed to be 2 orders of magnitude more precise than existing atomic clocks. So let me first explain how this device works and set up some basic equations for it, and then I'll formulate the purpose of my talk, the main question of my talk. So what we have here is about 1 million of ultra-cold rubidium atoms trapped in an optical cavity. So this clock utilizes an ultra-narrow transition line between the ground state and an excited state of this atom. So the atoms are pumped at a rate W, and then they decay, pumped to an intermediate level from which they decay to E. And then this 2-level system is coupled to a cavity mode with a Rabi coupling. So the atom then goes from E to G and emits a cavity photon. So each of the atoms is a 2-level system here. We describe it with 3 Pauli matrices, sigma X, sigma Y, and sigma Z. And because all 2-level systems are the same, they have the same splitting and are coupled to the cavity in the same way. So the Hamiltonian here describes a collective spin S subject to a Zeeman field omega, and then coupled to a single cavity mode. So this Hamiltonian is known as a decay Hamiltonian. So we also have to take into account the incoherent pumping and leaking of photons out of the cavity. So I didn't say here that it's a very bad cavity, and that's a key ingredient of this talk proposal, because bad cavity is insensitive to various sources of noise coming from the cavity, such as noise from the optical mirror. So we model the pumping and decay with this master equation. So the first term is Hamiltonian dynamics, the second term is incoherent pumping, and the third term is a decay of photons out of the cavity, where these curly L's are Limland operators. Now, because it's a bad cavity, the electromagnetic field in the cavity equilibrates with the atoms essentially instantly. So at a time scale, inverse decay rate equal to the inverse decay rate. So take a look at this equation for the expectation value for the cavity field, that follows from this master equation. So because this kappa is very large, expectation of A quickly goes to a constant, which is proportional to S minus. So in fact, you can show rigorously that at times much larger than kappa to -1, you can replace this photon annihilation operator with S minus times some constant. So this is a well-known procedure in quantum optics known as adiabatic elimination. So then we get an equation that is entirely in terms of spins, whereas this gamma c is the collective decay rate. So let's take a look at this master equation. So there are three parameters with units of energy in it. So by choosing energy units, we can get rid of one of them. So let's say we get rid of gamma c. So next we do system size expansion, using, for example, Carmichael's textbook on quantum optics. And to the leading order, we get these equations, these two equations, which you can also get just by a straightforward mean field. So these are equations for single classical spin, which is a normalized average of our quantum spin. Now, it seems like there are two parameters here, yeah, omega and w, but actually there is only one parameter because we can go to a rotating frame, a frame that rotates uniformly around the z-axis, and that will get rid of this omega. So we will be only left with w. So the system depends in an essential way on only one parameter w. So therefore, its phase diagram is going to be one-dimensional. And it's not difficult to prove that there is a single attractor here, which is a fixed point. Okay. And there are two phases. So for w greater than 1, the fixed point has S minus equal to 0. It means there is no radiation from the cavity. It's non-radiative fixed point. For w less than 1, S minus is greater than 0. So there is a macroscopic population of the cavity mode. And this transition that happens at w equals 1 is nothing but the superradiant transition. And superradiance is a coherent phenomena. So the field, the amplitude of the field is proportional to n, the number of atoms, and therefore the intensity is proportional to n squared. And this is the second and last key ingredient of this proposal. So the first one being bed cavity, and this superradiance is what allows to have sufficient intensity of this laser to have an atomic clock. So, yes, sure.
You get a question.
Could you please explain what is a quality factor? Does it mean that after 10 to the 18 seconds, it will deviate to 1 second, or what is it?
Something like that, yeah. Okay. Who cares what quality factor is? I mean, it's I mean, I actually don't know exactly how they define it, but the key thing is that it's 2 orders of magnitude better than existing clocks. Okay, so let me also comment on some certain mathematical properties of this equations of motion. So if we take the pumping, if we set the pumping to be 0, then these equations are nothing but the Landau-Lifshitz equation, and this second term is known as Gilbert damping. So what this Landau-Lifshitz equation does, it preserves the length of the classical spin, but it turns it to stay permanently along the field H. More generally, with a certain change of variables, these two equations map to what is known as damped Toda oscillator. So that's the equation for the damped Toda oscillator. And Payne-Levé integrability test for this equation shows that it's integrable only when W is equal to 0, no pumping, and W equal -1. Equal -1 is unphysical for our purposes, so it's integrable only at no pumping. All right, so I told you about one clock, and now I am in a position to formulate the main question. So where you have one clock, you can have two clocks, or you can have three clocks. And the main question you can ask about coupled clocks is, do they synchronize? Okay, so synchronization of clocks is a phenomenon that was first discovered by Christian Huygens. So with pendulum clocks. So he had pendulum clocks hanging from the same support, and what he noticed that their opposite swings coincide, at any point in time. So this is something that is known as anti-phase synchronization. And first he thought this is due to some air currents, but then, after a while he realized that actually it has to do with the support on which they hang. It's the imperceptible motion of that support. So also it was observed, and I guess by another member of the same Royal Society, who is Sir Baron Rayleigh. So he noticed that when two organ pipes of the same pitch, are side by side, they begin to speak in absolute unison, despite inevitable small differences between the pipes. So this kind of synchronization is known as frequency locking. So let's now look at two clocks in the same setup, in the same cavity. So again, it's a bed cavity and a photons leak to the environment. And again, we have incoherent pumping here. So here is a schematic energy level diagram. So you have pumping W, both ensembles are coupled with the same coupling omega to the cavity mode. But now, crucially, the splittings are different in the two ensembles because of inhomogeneous magnetic field. So now we have two parameters, two essential parameters, W, the pumping rate, and the detuning, which is the difference between the level splittings in two ensembles. So your phase diagram is now going to be two-dimensional. So this system actually of two clocks has been realized experimentally 4 years ago, and it has been studied. It and similar systems have been studied theoretically for quite a bit, with the conclusion that the phase diagram consists of just the same two phases as for one clock, and then a part of it there is some just nonsense. So when we started to work on this, there were two surprises. The first surprise, or maybe not surprise, is that all this work missed the most interesting and most important physics in the problem. And the second surprise was that actually the two clock phase diagram is incredibly rich. So besides the two phases that we saw for one clock, there are 5 other phases. And moreover, this system exhibits dynamics that is very rare in other driven-dissipative systems. So let me now briefly describe this phase diagram, what you see here. So first of all, you have this non-radiative normal phase and monochromatic superradiance. So here, the intensity of superradiance is going to be constant in time in this blue region. So these phases are the same as for one clock. But now you have this entire region 3, with all sorts of interesting behaviors. So overall, this region 3, can be summarized by saying that it's amplitude modulated superradiance. So what amplitude modulated means is that the intensity is going to depend on time, and it can depend on time in different fashions. So let us walk, along these arrows and see what we see. So first of all, we have a transition, or equivalently bifurcation, from this normal phase into symmetric limit cycle. So symmetric means that there is a certain Z2 symmetry between ensembles, and the limit cycle has this symmetry. Then along this dashed line, there is a transition from symmetric to asymmetric limit cycle. Now let's blow up this region near the origin and go along this other line. So, so there is an island of symmetric limit cycle here, which is actually different from the limit cycle, symmetric limit cycle here, but let's start in this island. Then we see these blue points. This is quasi-periodic behavior. So it means that in addition to one frequency of the limit cycle, another frequency appears, and then another, and finally the system becomes chaotic by way of quasi-periodicity. And now, most interestingly, close to this region 2, the chaos synchronizes. So what does it mean, the chaos synchronizes? It means that ensemble A, clock A, is chaotic and clock B is chaotic, but they follow one another. So in terms of synchronization, this phase diagram can be described as appearance, disappearance, and restoration of synchronization. So there are 3 different kinds of synchronized dynamics here. This region 2, just like for one clock, and then you have this question, limit cycle, and also this synchronized chaos. So most interesting out of these phases seems synchronized chaos to be. So let's focus on that, because hardly I can describe the entire diagram in a single talk. So first, let's set equations for 2 atomic clocks. So they are like 2 copies of single clock equation, except now each spin is coupled to L being the total spin. So you can think of them as 2 coupled Landau-Lifshitz equations plus pumping. So now let's identify the symmetries of these equations. So first of all, there is a symmetry with respect to rotations around the z-axis. Yeah. So rotation around the axis is multiplying S plus by a constant phase factor, and you see that it will cancel from this equation and from this equation. So it's symmetric. Now, secondly, you can complex conjugate these 2 equations. So the second equation is real, it will not change. And in the first equation, S plus will turn into S minus, and omega will become minus omega, essentially, right? Because I becomes minus I. So now, to reveal the symmetry here, it's best to go into a frame that rotates with the mean frequency, omega A plus omega B over 2. In that frame, omega A is equal to minus omega B. Okay, so when omega becomes minus omega, it's like A changing into B. You get an equation for S minus for B. In other words, you change plus into minus, and you change A into B, and the equations of motion, are invariant with respect to that. So, in particular, the 2 symmetric trajectories will have S plus A equal to S minus B, which in components means that the X components are equal, Y component of one is minus Y component of the other, and this transformation didn't touch Z, so Z are the same. Now, attractors, which I in this talk call phases also, and sometimes steady states, they can break one of the symmetries of both. I mean, that's one way how you can understand different phases in this diagram. So, and now we can give a precise definition of what synchronization of this clock means. So we say that A and B are synchronized when the steady state of the attractor is Z2 symmetric. Okay, then the two spins repeat one another, like the motion of one. Like by motion of one, you know exactly what the other is doing. So this is quite similar to the anti-phase synchronization. Here, the phase of one is equal to minus the phase of the other. The system has a reflection symmetry, about this median. So now here we replace pendula with spins and the median with XZ plane. So it's a symmetry with respect to reflection through the XZ plane. So, let's talk about synchronized chaos mainly in the remainder of the talk. So about its origin, experimental signature, and applications. So again, let's look at this region near the origin of the phase diagram. So there are two chaotic phases here. One is orange and the other is red. So chaos means that the maximum Lyapunov exponent is positive. Okay, so that will mean sensitivity with respect to initial conditions. Now, ordinary chaotic trajectories, they do not possess Z2 symmetry. And if you plot this attractor, is going to be 6-dimensional because there are 6 degrees of freedom. So it's going to occupy an extended region in 6-dimensional space. Now, so this Z2 symmetry is restored for these red points. Yeah. So that what it means that chaos synchronizes. So now to understand what's going on, let's project our equations of motion onto the synchronization manifold. So meaning that we impose Z2 symmetry. Yeah, we say our trajectory is Z2 symmetric. So then you get 3 equations out of 6, but these are not equations for one clock. So here they essentially depend on 2 parameters, delta and W, and there is no way that you can get rid of any one of them. So the phase diagram is still 2D, 2-dimensional, but just there are fewer phases. Okay, so the phases in this case are going to be symmetric limit cycle, chaos, and monochromatic superradiance. So, and in this reduced picture, synchronized chaos originates directly from the Z2 symmetric limit cycle along this dashed line. And to see what's going on, I mean, to determine this line, this dotted dashed line, you can do stability analysis of this limit cycle. So you linearize equations of motion around the limit cycle. And so this delta S are the deviations from the limit cycle. So now pick some point in time, and let's say the deviation at that point after n periods is delta Sn. Then the deviation after n plus 1 periods is equal to a certain matrix known as monodromy matrix times this delta S. Okay, so this is Floquet stability analysis. So this M has 3 eigenvalues, and the system becomes unstable when any of the eigenvalues in absolute value is larger than 1. Now it turns out that one eigenvalue is identically 1 because delta S equal to S dot is a solution of these linearized equations. This is because, linearizing the equations, taking delta and taking dot is the same. So you get the same equation. Therefore, delta S equal to S dot is always a solution. So there is one multiplier that is identically equal to 1 because it's equal to 1 because it's periodic. Yeah, because the limit cycle, this S, limit cycle solution is periodic. So S dot is periodic. So delta Sn plus 1 is going to be equal to delta Sn. Then we numerically find that one of the eigenvalues is always small. So this poses no danger. And then the remaining one, which is R2 in this notation, it goes through 1. It goes through 1 at this vertical axis, okay? So, don't pay attention to this dotted red line. This is another metamorphosis that happens to the limit cycle, like, the waveform changes, but it remains small or equal to 1. And then after this point, it becomes larger than 1. And so after this point, chaos ensues. So this kind of bifurcation, when one of the Floquet multipliers becomes greater than 1, is known as tangent bifurcation. So therefore, synchronized chaos comes directly from the Z2 symmetric limit cycle via tangent bifurcation. So near transition, the synchronized chaotic dynamics, these orange things, they are close to the Z2 symmetric limit cycle. But the Lyapunov exponent is positive, which means it's chaotic. So the fact, so the fact that it stays close to the symmetric limit cycle is important. So, but here is, how that bifurcation looks in Poincaré section. So Poincaré section is, you take your attractor and you cut it with some plane. So in this case, we look at the trajectory of one of the spins and we cut it with a plane as z equal to a certain value. And then each time the trajectory crosses that plane, you get a dot on this Poincaré section. So one color is for the trajectory going in and the other is for going out. So this thing with the discrete number of dots, that's clearly a limit cycle because limit cycle is periodic. So after some time, it will cross through the same point. So the number of points are going to be discrete and finite. So this is how synchronized chaos looks. So it's a continuum of points, but there is certain deformation and certain restricted sort of phase space volume, and this is how like full-blown chaos looks like. Okay. So, but this was restricted synchronization manifold. So now let's go back to 6 dimensions and let's see what happens with this picture in six dimensions. So the synchronized chaos, enters the picture at this dotted dashed line. But as you see from the full phase diagram, there is no synchronized chaos here. That's because it's unstable at its inception. So let's look at, for example, SZA minus SZB. For synchronization, this is going to be 0. So we are going to look, going along this arrow somewhere here, like after that dotted dashed line, after this line. So what we see that it's 0 for a while, but then there is an outburst. And then again, it's close to 0. So, but as we come closer and closer to this phase 2, these outbursts become smaller and smaller. So both their frequency and the magnitude decrease. yeah, until chaos fully synchronizes. And this has this red points. So this is tangent bifurcation intermittency, and synchronization occurs via on-off intermittency. So, and another measure of chaotic synchronization is the conditional Lyapunov exponent, lambda c shown here. So don't pay attention to this blue and orange curve. So this green one is for synchronized chaos. So it's chaotic. So the maximum Lyapunov exponent is positive. But conditional Lyapunov exponent, that's a Lyapunov exponent for directions transverse to the synchronization manifold. Yeah, to the directions in which synchronization occurs. That one is negative. So in those three directions, it's not chaotic. Okay, so let's talk about experimental signature of synchronized chaos. So the observable here is an autocorrelation function, which is the same, the power spectrum of radiated electric field. And so that can be measured with Michelson interferometry. So this is proportional to total spin L minus at frequency f mod squared. So each of the phases that I described has a unique signature in the radiated power spectrum, but I will only describe the signature of the synchronized chaos. So here is the power spectrum for synchronized chaos. So first of all, it's continuous, which is indicative of chaos. And how synchronization manifests is that the spectrum has reflection symmetry, about the origin. And this reflection symmetry is because by Z2 symmetry, SYA is minus SYB, so LY is 0, which means that L minus is real, and the Fourier transform of a real function has this reflection symmetry around the origin. Secondly, if you blow up this, you see that actually there is no peak at the origin. And this is leftover from Z2 symmetric limit cycle, which only has odd harmonics, so it doesn't have a peak at 0. So if you compare this to ordinary chaos, so you see that there is both a peak at 0, and you see that there is no reflection symmetry in the ordinary chaos. So like, for example, this shoulder is lower than this shoulder. So that's how you can tell synchronized chaos. And finally, let me mention one application. So there are different applications for synchronized chaos, but the one I found most interesting is steganography. So the purpose of steganography is to hide the very fact that you transmitted any message. So not just to encode the message, but to completely hide its existence. Okay, and so here is how it should work. So you have this, let's say, ensemble A. That's our chaotic carrier. So it has certain show some chaotic line, but then ensemble B has the same line. So it has the same line. And then you add a perturbative small message on top of this carrier, and that gives you a signal, but then ensemble B also has the same signal. So it has both the original signal and the new one, and so it can subtract and get the message. So that's the idea of using synchronized chaos for steganography. So, and I should say that synchronized chaos, I think I didn't voice that, is quite rare, especially in systems with bidirectional coupling, meaning, so, there are like proposals of synchronized chaos in master-slave scenario when system A is not influenced by B and only B is influenced by A, like some variable from A is fed into B. But what we have here is bidirectional coupling where A influences B and B influences A. And to have synchronized chaos in that scenario is quite hard, and there are not many examples. And especially in a cavity QED, which is very controllable environment, it has never been sort of theorized, predicted, or observed. So, that was the main part of my talk, but I kind of cannot resist to give you, because I find it rather, amusing, to use this phase diagram as a tutorial on bifurcation and chaos frequency. So, that will kind of underscore how rich it is. So there are all sorts of bifurcations here. So going from 1 to 3, this is known as supercritical Hopf bifurcation. Supercritical means that the limit cycle, it's like a second order phase transition. From 1 to 2, it's supercritical pitchfork bifurcation, because you have one fixed point, but then it splits into 3 like a pitchfork. It's 3 because here S minus is non-zero and it can have plus and minus sign. In our convention, it's always real, but it can have plus or minus sign. And the third one is this S minus 0 fixed point, which is still continued, but is unstable. Okay, so now, let's walk along this arrow. So Z2 symmetric limit cycle to asymmetric limit cycle, this is supercritical pitchfork bifurcation for the Poincare map. And then asymmetric limit cycle into the quasi-periodicity that is known as torus bifurcation. So the system first lives on a circle, now it lives on a torus, now the dimension, and then the dimensionality of torus increases further. The transition from quasi-periodicity to chaos, this is quasi-periodic route to chaos. So the usual route to chaos is period doubling, but this is different. This is quasi-periodic route to chaos. And now chaos to synchronized chaos is, as we discussed, tangent bifurcation of the symmetric limit cycle. And now one last surprise, going from 2 to 3 is subcritical Hopf bifurcation, similar to first order phase transition. So such a bifurcation is known as catastrophic bifurcation, because after it, the system, immediately after it, the system is very far from where it was before. So that's a catastrophe. And also it implies coexistence. And indeed, there is a coexistence region here, which is, this small violet sliver. That's a coexistence region where here, for example, 2 and symmetric limit cycle coexist, and synchronized chaos also can coexist with 2. Okay, so this brings me to the end of my talk, and I should mention my collaborators. So, most of this work was done by my former student, Aniket Patra, who I think is in the audience now and who is now in Denmark, a postdoc. And also, we had a lot of useful discussions over tea with Boris, Aniket, and me. And this talk is based on these 3 papers that you see here. Thank you very much. So I didn't mean to discourage questions by, answering about the quality factor, maybe somewhat.
A simple question about the spectrum that you showed. So there was some noise apart from these peaks I mean, the whole thing looks a bit noisy. Is this due to the fact that it's computed for a finite total time? Or
so this is spectrum.
yes.
I don't know for sure. I can answer that better, but I think it's just a numerical. I mean, in principle we could run the system for very long time, but where do you see the noise, though?
I mean, just if you look closely, there looks like there is some noise. Maybe it's not actually.
I don't know, but the other spectra, like for limit cycle, it looks perfectly equidistant, and for quasi-periodicity, I didn't show those, looks discrete. So I mean, this, like, you immediately see it's a chaotic spectrum.
Yeah.
But I don't know about the noise. I mean, certainly numerically, I mean, the precision can be increased and increased and increased here.
And then it would become more smooth between the peaks.
Yeah. So you want, yeah, maybe. I'm not sure actually if it becomes smooth.
I have a silly question. How does one measure the negative frequency component of power spectrum? You have radiation coming out of the certain frequency.
Yeah.
How do you tell positive frequency from negative?
So it's a Fourier transform of an autocorrelation function, which is like, E at t and E, like E conjugated at t, E at t plus tau.
Okay.
So,
Right.
so that's what.
So essentially, you need to measure the electric field dysfunction time to be able to do this.
Yeah, that's what Michelson interferometer does. Like, it sort of has a different pass. Like you split it into two, and then like I think that's what they do. And I think they just measure the Fourier transform, not that they have to measure it as a function of time and then take, but it just, the interferometer is made to give just that Fourier transform.
And I guess you need to look at two polarizations.
Why?
Which are like real and imaginary part.
Two polarizations. Yeah, maybe. Yes, please.
So where is precision factor of 200 comes from?
Like 100, you mean?
I said 200.
This is, yeah, maybe I misspoke, but 2 orders of magnitude, that's what they say. So, I mean, I kind of spent some time talking about this thing as a clock, but for what I have, it's not actually important that this is a clock. Okay, but it comes from the following reason. So this quality factor 10 to the 18, it has to do with this, with the width of this line. The line is ultra narrow, and that's the fundamental limit. Now, existing lasers, they also use this line, but you have to bring external lasers to have sufficient output, and these external lasers bring noise. Here, the idea is to use this transition directly without external lasers, with the help of super radiance, that it will have enough intensity for that. So that comes from there, from that. But this has been proposed, like almost 10 years, I think, ago. And yeah, I don't know if it's going to be built or not.
Why it was not built? Great question.
So this device is an actual experimental thing, and so that's a proof of principle that it can be built. But I don't know. I mean, maybe it's very expensive. Maybe I just don't know why. There are many things that can be done. but are not done not for fundamental reasons, but for technical kind of reasons.
Which transition? Which transition?
It's for Zoom people, it's not for us.
Yes, which transition? Yes.
You mean like which are the quantum numbers of this level? I don't know. I mean, we can look it up in the paper. I'm not sure they describe like precise atomic sort of levels.
Guys from internet, Florian and Christoph,
Yeah.
can you build this thing?
Yes, I can comment a little bit perhaps.
Yeah.
So I know a bit about the Gilla experiments. So the clock is run with strontium atoms that have an intercombination line, which is very narrow and which has a very high quality factor. The quality factor is defined to be very loosely. It's sort of the transition frequency divided by the line width of the transition. And now I mean, it's well known what the transition frequency is, but what is the line width? And that's to be discussed. Yeah, I mean, usually it's actually the line width that you get because you have a finite interrogation time. Yeah, you artificially broaden the line by it's called Fourier broadening. So this is done with strontium atoms, yeah, on a singlet to triplet transition. Rubidium doesn't have such a transition. So rubidium can be used as a test bed, perhaps, and we put in a cavity for testing things. And on rubidium, you can certainly build a clock on a hyperfine transition, so a microwave transition, but that's totally different and has a much lower quality factor. And that's certainly not an optical transition. So I think there are now two things here. Yeah, the rubidium experiment and this actually the very precise clock built by Juni with strontium, with fermionic strontium actually in a lattice. It's a lattice clock actually, the most precise one so far. So that's what I can say in a few sentences here.
But there are atomic clocks that use rubidium too.
Yeah, secondary standards. Yeah, they do microwave. Yeah, they at the about 6.8 gigahertz. They interrogate the hyperfine transition, the ground state hyperfine transition, and there are various variants. Actually, a lot of the commercial clocks you can buy are actually rubidium clocks, but it's I mean the quality factor is certainly orders of magnitude less than the most modern optical clocks. So optical means that the transition is not a microwave transition, but it's really an optical transition. The transition in strontium is somewhere near 700 nanometers or so, so in the red. And that's then interrogated by a super narrow laser. Actually, the laser on short term is really very stable. The fractional instability, as if I remember right, is at the level now of 10 to the minus 16, averaged over a second. And that then averages down with the square root of T behavior towards 10 to the minus 18 after a few hours. Yeah, and the hope is to get to the level of 10 to the minus 20 when averaging across a few hours.
I just realized somehow something happened with the reference. So here is actually the paper.
Yeah, this is actually, this is from the Thomson group. And this is, I would say, this is a proof of principle experiment on rubidium. Yeah,
exactly.
I mean, for sure, very nice. Yeah, but it's that's actually where you take the photo from. Yeah,
exactly. Yes.
Yeah, and it shows actually here in figure 2, it shows on the left, it shows a typical level scheme that you could use on strontium, terbium, or calcium, all these 2 electron systems or effective 2 electron systems where one has these super narrow lines. Yeah. On rubidium, one would have to drive something else. One could do something like a Raman transition or so, a 2-photon transition. These can be very narrow. That's indeed true. Yeah. So and that could be used. So I actually don't know how good this works for rubidium. Yeah, but it would have to be a 2-photon transition then.
Right. Yeah. So this is a nice paper. And here are the levels, I mean, that you asked about. So
Yeah, that on the left, that's this optical clock idea, singlet, triplet, and on the right you can see this Raman type situation, yeah, V type. I mean, I don't know the details of this now here, so I cannot comment anymore. I would have to read about it.
okay, thank you.
Okay, welcome. Yeah.
Yeah. So the question is whether people don't want to build it so much, or they can't really want very much, but can't really, right? Anyways, yeah.
So I think I missed what's the experimental proposal to make the two clocks? What corresponds to the clocks A and B?
Clocks are just, you see, there is this ensemble like of atoms that are trapped in the cavity. So if you have two ensembles that are trapped, that's going to be two clocks.
And why is because the atoms behave independently within each ensemble. I mean, they're only coupled through the cavity, right?
Yeah.
So why is it then different to have two clouds as opposed to one cloud?
Because that's just where they are located.
Okay.
So, so the whole system is in the homogeneous magnetic field of the trap. So if the two clouds of atoms are located at different positions, they will have different splitting.
Okay.
And that's what will make them different. Otherwise, it would be one clock.
Okay, thanks.
Yes, but in real life, we could imagine to have actually as many clocks as atoms with each its frequency. So would your theory
It would be very interesting. I mean, with that system, we didn't start. I mean, complex many-body system. So if we had many clocks, that would be very interesting. That's going to be a complex many-body system. I mean, we thought a bit about it, and we think that certain phases are going still to exist. So, I mean, like certainly the chaotic phases and symmetric and the limit cycles. So it would be very interesting. So the two clocks they already built, and for two clocks they can definitely observe what we talked about. So they are citing us, but I haven't seen them actually doing it, though they could do it.
Yeah, Christoph. So we see you. You want to say something on the main screen, or it's just no? I don't know. Anyways, in such a case, I stop recording. If we don't have other questions, we don't.